And welcome to the lecture 7 of the Electrical Circuits 1 course. Today we'll start on the introduction to mesh current method. But before we start that, let's do one more example from the node voltage method and we'll build up from there. So this is the example we're going to start with. So this current source is 4.8 ampere and this voltage source is 12 volts, and we are asked to determine the voltage across this 10 ohm resistor. So let's say voltage across 10 ohm resistor is V, and this is a current controlled voltage source, and that current is dependent on the current flowing here, so Ix. So that is the question, and these resistors have values of 2.5 ohm, 7.5 ohm, 2.5 ohm again, and then this one has 1 ohm. So as usual, let's start with the question. How many nodes are there? Yeah, if you guessed 5, that is correct. This is the one node, this is another node, this is another node, this is another node, and this is another node. So with that, how many independent nodes do we have? So considering the base, this is the reference node, and if we have V ref is equals to 0 here, this will be 12 volt. So the only 3 nodes that we don't know the value of voltages will be those 3. So those will be the 3 independent nodes, and let's call this as Vx. This is the voltage V because we need to determine this voltage V here. So call that V, and then we'll call this one, the last one, as VUI. Okay, so let's erase this. This is the VUI. So that is the voltage. So now we could use KCL at this voltage source here, this node, but there is unknown current in this current controlled voltage source. And whenever we have 2 or more reference nodes with unknown voltage, and we have a dependent or independent voltage source, in those kind of situation, it's easy to use a concept of supernode. So let's do that here because that will make the problem easy. So we have 2 unknown nodes, non-reference nodes, and in between those we have this voltage source. So whenever we have this kind of situations, we can use a concept called as supernode for this. So supernode. So let's start with that. So whenever 2 non-reference nodes are directly connected by a dependent or independent and voltage source, it is convenient to apply the supernode concept. So, and a supernode is basically a closed surface, and KCL, or Kirchhoff's current law, applies to the surfaces too. So now we assign current directions. Assign current directions and polarity using the passive convention. So we do that using the passive convention, and we write the directions. So let's say this is positive, this is negative, so current is following this direction, positive, negative, this is already positive, negative. Let's say the current is flowing this direction, positive and negative, again this direction, positive and negative. So now we have that, we can start applying Kirchhoff's current law at the supernode. In the supernode here, the incoming current will be this current, which is the Vx minus V divided by this 2.5, and outgoing currents. So this voltage is V. So V divided by V minus 0 divided by 10, that is one of the outgoing currents. The other one is Vy minus 0 divided by 2.5, and we have third outgoing current, which is Vy minus this voltage, which is 12 volts divided by 1 ohm resistor. So basically write that one down here, KCL at the supernode. So we write KCL in terms of voltage. That was the second step, right? Supernode, KCL at supernode. So Vx minus V divided by 2.5, that is the only incoming current, is V minus 0 divided by 10 plus Vy minus 0 divided by 2.5 plus By minus 12 volts divided by 1. So if we simplify this, you will get minus 4Vx plus 5V plus 14By is equals to 120. So let us call this as equation 1. Now we can also do KCL in this node X here, and then we'll have this 4.8 ampere current going in, we'll have this current going out, which will be Vx minus 0 divided by 7.5, and we have other current going out, which is Vx minus V divided by 2.5. So let's do that. KCL at node X. So what we'll get is 4.8 is the entering current, and the current that exits is Vx minus 0 divided by 7.5 plus Bx minus V divided by 2.5. So if we simplify this again, we get 4Vx minus 3V is equals to 36. So that will be our equation 2nd. So that will be our equation 2nd. Now we have two equations, but we have three unknown, Vx, V, and Vy. So we need one additional method to get a system of equation, so that we can apply the equation and solve the system of equations. So now to get the other variable, we can get equation using the Kirchhoff's voltage law, and that we can do around this supernode. So if we look in there, and if we do a KVL here, so here this will be going from negative to positive, so that will be minus V voltages, and this is a constant, this is a voltage source, so that will generate Ix volt, which is again going from negative to positive, so minus Ix, and then we have this Vy, which is going from positive to negative, so plus Vy. So if we do that, if we apply KVL at supernode, so we apply KVL at supernode, what are we going to do is we'll get minus v minus ix plus vy is equals to 0. So this will be our third equation. Now we have three equations, but at the same time we introduce a new variable ix. So what can we do is, now we have dependent source, and every time we have a dependent source, we can relate that dependent source to another dependent variable to get another equation. So in that case, dependent source is ix, and we have to figure out a way to relate this ix to the voltages that are already coming in the equations. So here what I can do is we can use the Ohm's law between these points to calculate ix in terms of vx, because we already have vx in earlier equation. So that ix will be, ix is basically vx minus 0 divided by 7.5. So if we use that, we use the dependent variable. So we have the dependent variable, which will be ix is equals to bx minus 0 divided by 7.5. And if we write that simply, that will be bx minus 7.5 ix is equals to 0, and that will be our fourth equation. Now we have 4 equations and 4 unknowns, so we can write that in matrix form and solve the equation using either directly using calculator or manually, or using Cramer's law for matrix problem solving. So first let's write that into matrix format. If we write into matrix format, we'll have 4 unknowns, which are vx, b, vy, ix is equals to so from the last equation we have 0, third equation we have 0, 36 and 120. So 120 and 36. Similarly, we have 1, we have minus 7.5, but for v and vy we have 0, 0. So we don't have vx, so that is 0. We have minus 1, we have 1, and we have minus 1. And similarly we have 4, minus 3, 0, 0, and we have minus 4, 5, 14 and 0. So we can, this is in the form of ax is equals to b. So you can solve it any way. You can calculate the inverse and do solve for x, or you can apply Cramer's law or whatever. So, or you can use directly your calculator. So I'll just write the answer. So you can solve this. What you'll get is, you'll get vx is equals to 15 volts, b is equals to 8 volts. You'll get vy is equals to 10 volt, and you will get ix is equals to 2 ampere. So this is the voltage across the 10 ohm resistor. Resistor, and we were asked to find this value, so that is our answer. So this is still the node voltage method we are solving. So now we'll move to another very important method, which is mesh current method, or sometimes it is referred to as loop current method. So loop current method or mesh current method is a generalized technique which is valid for planar circuits. So mesh current method. So mesh current method is a generalized technique valid for planar circuit. So So this is a very special condition. So maze current method is always valid only for planar circuit, and there was no such restriction for the node voltage method. In all the circuit analysis course, especially part 1 and part 2 will take, we never deal with circuits other than planar circuits, so there is no exception in this class. But in real life situation, when you're dealing with a complicated maze that go into 3D, so we cannot apply the maze current method, and we'll have to rely on the node voltage method. So that's it. Let's define planar circuit. So basically this is a circuit. This is a circuit where no elements cross each other. Or saying simply, you can draw a two-dimensional plane paper sketch for circuit analysis. So that's all. Similar to the node voltage method, maze current method has some set of procedures, and if you follow those steps thoroughly, there is no chance you'll make a mistake. So I'll write this down, and we'll do some examples to solve the maze current method. So procedure. So the first step here, is to define currents. Define currents flowing in the meshes of planar circuit. Okay, so that is the first step. Second one is we write the Kirchhoff's voltage law around the meshes using Ohm's law to express voltages across the resistors in terms of the maze current. So in the node voltage method, what we did was quite opposite. We wrote down the KCL around the nodes using Ohm's law to express the current across the resistors in terms of voltage. And that was the method. Here we are writing the KVL around the meshes using Ohm's law to express voltage across the resistors in terms of mesh current. So the third step here is using KVL we'll get equations, and we solve those equations to get the unknowns. So we'll solve the system of equations. So we solve the system of equations, and finally using the mesh currents, we find the desired electrical quantity. So these are the 4 steps that if you follow thoroughly, you'll be able to solve the problems using maze current method. So let's start with one example. So we have the resistor, another resistor, we have positive, negative. This is 20 volts. Another resistor, another resistor, and then we have another voltage source which has 60 volts, and we have a resistor here too that is 10 ohms. This is 2 ohms, this is 3 ohms, this is 1 ohms, this is 4 ohms. When you are starting the circuit analysis, one of the mistake I usually make is when copying the problems, I usually make sometimes make mistakes in the polarity. So if you have same polarity, if you have a given polarity and one of the voltage source, doesn't mean it will have the same polarity in another one. So make sure you are copying it correctly, otherwise your analysis will be ruined. So now we follow the steps of the mesh current method to solve the problem. Now the first step was defining the currents. So define currents. So define currents. Here we can simply say, because we have just two meshes, we can simply say this is I1 and this mesh current, and this is as the I2 mesh current. And what the problem is actually asking us to do is determine those currents IA, IC and IB. But before doing that, we have to define the currents and use the sign conventions to give the polarity of the passive elements. So for the outer surface, we can do this as usual, assuming the current goes this way. So it will always be this, and we'll leave the inner 10 ohm resistor for now, because that the current direction depends on which mesh we are considering. So now move to step 2. Step 2 is doing the KVL. So let's start with the KVL on the KVL around the left mesh. So on the left mesh, you can see that if we follow this direction, we have minus 60 because we are going up in the clockwise and it's going from negative terminal to positive, and we have 4 times I1, okay, and then we have 10 ohm resistor which has currents. So for 10 ohm resistors it's different, because here we have I1 is going down this way, which is positive, but in reference to I1, I2 is going in the opposite direction, so that is negative. So they cancel out each other, and hence they don't cancel out each other, so they are in the opposite direction, so we take the opposite sign. So I1 is in the direction we consider clockwise, minus I2 is in the opposite direction when looked for the mesh. And finally, once we are here, we have 1 ohm resistor with I1 current. So that is our first equation. Similarly, we can apply KVL around the right mesh. So if we do that, let's start from this 2 ohm resistor where we have 2 times I2, because that is the mesh current. Now we are going from positive to negative terminal, so we have 20 voltage plus 3I2, and we are closing the loop by going to this 10 ohm resistor where I2 is in the positive direction as looked from the right mesh, but then I1 is in the opposite direction of I2, so we have to subtract I1 for that resistor. That again gives to 0, so which is our second equation. So we have 2 equations and 2 unknowns, I1 and I2, so we can solve those. So step 3 was solve the system of equations. So if you solve this, you can use calculator or just manually do it. You will get 5.6 ampere for I1, and for I2 you will get 2.4 ampere. So our final step, step 4, was using the mesh current currents, find the desired electrical quantity. So now we can write IA, IB and IC in terms of I1, I2 and I3. So here IA is equal to I1 because they are in the same direction. IC is in the opposite direction of I2, so IC is basically minus I2. And IB, if it's following this direction, it will be I1 minus I2. So we can now get the required currents using the mesh currents. So IA is I1, that is 5.6 ampere. IB was I1 minus I2, which is 5.6 ampere minus 2.4 ampere is equals to 3.2 ampere. And finally IC is equals to minus I2, which is equals to minus 2.4 ampere. So this solves the problem using the mesh current method. Let's do one more little bit complicated example. It is mostly the same as this example, but we'll also introduce a constant current source. As I mentioned earlier, look into the polarity of these sources. So it's negative, this is positive. And this is positive, this is negative. So this is 20 volt. And we have a current source which is 6 ampere here in between. And we have this is 4 ohms, this is 9 ohms, this is 6 ohms, this is 1 ohm. So what we have to do is find the mesh current. So let's say if this was I1 and if this was I2, we are just required to calculate the values of I1 and I2. That's all. So let's follow the steps again. So the step 1 was defining the currents, right? So define currents and polarity or current direction using the passive convention. So for the passive elements, just consider outer loop, plus minus, plus minus, plus minus, plus minus. So that is it. Step 2 was to apply KVL, right? So apply KVL. We could apply KVL, but this 6 ampere current source is an independent current source, and that always produces a 6 ampere. So if we are trying to relate that to I1 and I2, that will just make complicated. And we all can also do this because we also don't know the voltage across these ends. So in these situations, we have two non-reference nodes such as this, and a current source similar to the node voltage method, if you have two non-reference nodes and then a dependent or independent voltage source, we introduce the concept of supernode. Here similarly, if we have a current source and if we have non-reference nodes, we introduce the concept of super mesh. So super mesh is basically a closed path in circuit that does not include the current source. Let's write it down. Super mesh. So super mesh is a closed path in the circuit that does not include the current source. So in our case, it will be the outer loop, because the inner loops, they have the dependent, they have the current source. So in our case, the super mesh will be this mesh. So the outer mesh, this will be the super mesh. Now we can apply KVL at the super mesh, and if you just look into the outer branch, so this will be, if we start from here, this will be minus 20 volt, because it is negative, this is positive. We go there, this is 4 times I1, it's 9 times I2, which is both are positive, and then here it's negative to positive, so that will be minus 90 volt. Then we have plus 6 times I2, and we come around here, and that is 1 times I1. So we can write it down, and we can write it down as the KVL at super mesh. So that was minus 20 plus 4 times I1. On the right hand we had 9I2, and the polarity goes from negative to positive for 90 volt source. So minus 90 plus 6I2, and finally have 1 times I1 is equals to 0. Or if we simplify this equation, we'll get 5I1 plus 15I2 is equals to 110. Let's call this as equation 1. So with the super node, whenever we wanted to determine another variable, what we did was we applied KVL. But here for the super mesh, we apply KCL to get the unknown parameter. So for that we try to relate the current source to the other unknown parameters. So here the unknown parameters are I1 is following this direction, and I2 is following this direction related to the 6 ampere source. And we know we can just look at this and conclude that the 6 ampere is related to I1, and I2 is 6 is equals to I1 minus I2. So basically that is what we're going to write as a Kirchhoff's current law at the current source. So we write Kirchhoff's current law at current source. So if we write KCL at current source, that will be I1 minus I2 is equals to 6. That is our second equation. And now you can solve equation 1 and 2, and you should be getting the values of I1 and I2, because that was our step 3, right? Solving the system of equation, and we have 2 unknowns and 2 equations, so we should be able to solve it. So you solve I1, I2, you'll get I1 is equals to 10 ampere, and I2 should be 4 ampere. So yeah, so this is a basic analogy. In the next class we'll discuss the node voltage versus mesh current, and try to solve the same problem using 2 different methods, and analyze which method gives the efficient way of solving these kind of problems. Thank you, and I'll see you in the next video.